polarizers, linear polarizers, circular polarizers, elliptical polarizers. Today we're going to talk about polarization in the first and final episode of Physics for Fools. Before we get into polarization, it is important that you guys first know the basics and understanding of electromagnetic waves. Alright then, here we go. A wave with an electric field and a magnetic field perpendicular to each other, propagating through space while carrying an energy, is an electromagnetic wave. Electromagnetic waves range in frequencies and wavelengths, and these are presented by the electromagnetic spectrum. Now, the small visible portion of the electromagnetic spectrum between the wavelengths of 400 to 700 nanometers is light. The primary properties of light are intensity, which is brightness, propagation direction, which is the direction of travel, wavelength, which is the distance between two successive crests, frequency, which is the number of waves passing a fixed point per second, and polarization. Now, by definition, polarization is referred to the direction of oscillation of the electric field in the transverse plane. Now, that sounds kind of confusing, right? Well, here's a video to give you a better understanding. But wait, if the orientation doesn't impact the polarization of the light, how can you have unpolarized light? Well, a light beam from a light source, let's say the sun, contains multiple light waves. These light waves have different properties, including polarization, as compared to the other light waves in the light beam. In fact, there are that many differentiating light waves that the polarization of the light beam is said to be indeterminate, thus stating the light beam to be unpolarized. Hey, wait, why is the polarization based on the electric field and not the magnetic field? This is because electric fields interact with atoms, whereas magnetic fields do not. You can think of it as atoms being made up of charges, and that charges respond to electric fields, hence showing that atoms respond to light. That was polarization. Now, a polarizer is referred to any device that can select plain polarized light from an unpolarized light source. So, when and where did all this polarization thing come into discovery? Believe it or not, but Vikings were the first one to discover the polarizing phenomenon. After the Vikings traveled to Iceland, they discovered a rare material called Iceland spar, which is a transparent form of calcite. They were fascinated by how light behaved in these crystals. The ancient discovery of calcite is still a preferred material in splitting polarizing components of light in modern science. But since this wasn't really reported or documented, we cannot consider this information to be reliable. Fast forward a couple hundred years into 1669, where we get the first hint of polarization. Erasmus Bartholin noticed that a clear, colorless calcite crystal, also known as Iceland spar, created a double image when objects were viewed in it during transmitted light. Another thing that caught his attention was that when he rotated the calcite crystal, one image would move around the other in a circular motion, as if the light was being split into two separate beams. In 1808, the French mathematician Étienne-Louis Malus had a major contribution to the discovery of polarization. One evening, he obtained the reflection of sunlight through his window pane into a calcite crystal and found that the two images that were created varied in intensities as the calcite crystal was rotated about the line of sight. From this, he formulated Malus's law. Real creative, right? And this is the proportionality of intensity of the light by a polarizer to the square of cosine of the angle of direction of the transmission axis for linearly polarized incident light. The way you see this on his formula is I, being the resultant intensity, is equal to I max, which is the maximum intensity of the light without a polarizer, multiplied by cosine squared of the angle between two polarizers. Not long after, in 1812, Sir David Brewster described the features of polarized light. He discovered the law giving the relationship between the refractive index of a medium and the angle of incidence at which the reflected light is totally linearly polarized, and that the angle of reflection and the angle of the refracted ray is perpendicular, thus naming the special angle Brewster's angle. Again, real creative. Something else that Brewster also discovered was the kaleidoscope, which, if you don't know what that is a visual instrument made by mirrors at an angle such that the created image is a geometrical, symmetrical pattern, which in my opinion is actually pretty cool. With a keen interest in polarization, French scientist Francois Arago worked with Augustin Fresnel to investigate the interference of polarized light. They discovered that two beams of light polarized with vibration directions oriented perpendicularly do not undergo interference. He also developed the very first ever polarizing filter, which was made by compressing glass sheets together. Polarization had advanced significantly after that time. In 1932, Dr. Edwin Land had invented the first commercially available polarizing material made from synthetic films. And these synthetic films came under the name Polaroid. Later in 1948, A.F. Halleman coined the phrase Polaroid or polarizer as any device that selects a plain polarized light from an unpolarized source. Okay, that's enough of history. Let's go back onto polarization. Oh damn! I forgot to explain how polarization works. I'll show you this by showing the rope and fence analogy. Before I cover the analogy, I would like to point out a common misconception. People with limited understanding of polarization state that half of light is blocked off as a polarizer only allows that one dimension of travel of light. And that must mean that either the electric field or the magnetic field passes and the other field is blocked off. For those who know this, I'm sorry to say, but this is actually seriously wrong. I'll give the correct interpretation now. The rope represents the electric field and the fences represent the polarizing filters. Looking at the left, two vertically oriented fences, we can see when the rope is vibrated vertically, the rope oscillates throughout. But if we take a look at the right two fences with different oriented fences, when the rope is vibrated vertically, the first fence lets it through, but the second fence completely stops the rope from oscillating. The same behavior occurs for polarized light onto another polarizing filter. A more practical representation can be seen throughout this video. Remember how I said before atoms respond to light? Well, electromagnetic waves specifically. In a solid, when light interacts with these atoms, they vibrate, causing it to heat up. Polarizers do not, I repeat, do not work like this. In fact, they work more like glass. They transmit light. They don't really hold on to it. The molecules in a polarizer form long chains, which is tightly bound. This limits them to vibrate only on one axis. This axis is the polarization axis, and it is found perpendicular to the chain. Even if we were to send a light that isn't polarized to this polarization axis, it would still cause the atom to vibrate in this direction. I know this is overwhelming, but hold on. The acceleration of the electron in the atom will generate the outgoing light. And because the acceleration of the electron was only in one dimension, the polarization axis, the emitted light is polarized. And we get polarized light. Scientists have found that there are 4 ways to polarize light. And by polarized, we mean linearly polarized. And these polarizations can be achieved through transmission, reflection, refraction, and scattering. Transmission is basically just shining a light through a Polaroid or polarizer filter. Polarization by reflection can be achieved by all surfaces except for mirrors or any metallic surfaces. Polarization by refraction can be achieved through the refraction of birefringent materials or surfaces. These are usually glass, water, or even crystals. Polarization by scattering can be achieved as when electrons accelerate, they emit a light. But keep in mind though, that the acceleration of the electron is random, and due to this, it causes the emitted light to be random as well with their own polarizations. Hence the name scattering. Now you guys probably remember, what the hell did I scream about in the beginning of the video? About circular or elliptical polarizers? Well, I'm going to explain that to you now. Remember how we said that the sum of the polarization can be represented as the sum of the vertical and the horizontal component of the polarization? If we were to slow down one axis of this polarization, we can result the amplitude to be out of phase with the other component. And if we were to add back these amplitudes, we will receive an elliptical shape. If we were to be more specific and say that we slow down one axis of polarization by exactly quarter of the wavelength, we can achieve a circularly polarized light. And the name for the special polarizing filters that give out these shapes are elliptical and circular polarizers. In fact, these polarizations can be demonstrated by a model.
Polarized sunglasses, so imagine you're standing near water, or maybe you're standing on ice or snow or something reflective. There's a problem. Say the sun's out, it's shining, it's a beautiful day, except there's going to be glare. Let's say you're looking down at something here on the ground. Well, it's going to get light reflecting off of it from just, light's coming in from all directions, but it also gets this direct light from the sun. So it gets light from reflected off the clouds and whatever's nearby, ambient light. And then there's also this direct sunlight. That's harsh. If that reflects straight up to your eye, that hurts. We don't like that. It blocks our vision. It's hard to see. It's glare. We don't want this glare. So what can we do? Well, it just so happens that when light reflects off of a surface, even though the light from the sun is not polarized, once it reflects, it does get polarized, or at least partially polarized. So this surface here, once this light reflects, it's coming in at all orientations. You got electric field. You never know what electric field you're going to get straight from the sun. And when it reflects, though, you mostly get, upon reflection, the direction of polarization defined by the plane of the surface that it hit. So because the floor is, horizontal, when this light ray hits the ground and reflects, that reflected light gets partially polarized. This horizontal component of the electric field is going to be more present than the other components. Maybe not completely. Sometimes it could be completely polarized, but often it's just partially polarized. But that's pretty cool, because now you know what we can do. I know how to block this. We just get some sunglasses. We put some sunglasses on, and we make our glasses so that these are polarized. And how do we want these polarized? I want to get rid of the glare. So what I do is I make sure my sunglasses only let through vertically polarized light. Here's some polarizers. That way, a lot of this glare gets blocked because it does not have a vertical orientation, it has a horizontal orientation. And then we can block it. So that's one good thing that polarization does for us in understanding it. We can get rid of glare. Also, fishermen like it, because if you're trying to look in the water at fish, you want to see in through the water. You want to see this light from the fish getting to you. You don't want to see the glare off of the sun getting to you.
I have conducted an experiment to see how the resultant intensity of the light is related to the degree between two polarizing filters. Polarization experiment. Aim: to investigate and test how the angle between two linear polarizers affect light intensity. Now, the materials required for this experiment are one incandescent light source, two linear polarizers, two base and retort stands, one protractor, one light meter, and one 30-centimeter ruler. Now, the risk assessment for this particular experiment. The equipment: incandescent light. Risk: the light can be blinding. Precaution: do not look directly at the light. Another risk from the equipment: incandescent light source. Can fall and break, causing cuts and injuries. Precaution: place light source in the center of the table. Method: 1. Set up the incandescent light. 2. Attach one linear polarizer with the protractor. 3. Set both linear polarizers with a retort stand such that it is in line with the incandescent light. 4. Set the light meter right behind the polarizing lens such that it faces the light. 5. Set the angle between the two polarizers. 6. Turn on the light and record the reading on the light meter. 7. Write down the results in a table. 8. Repeat steps 4 to 7 until all results have been recorded. The variable table. The independent variable is the angle, and this is measured in degrees. The dependent variable is light intensity, measured in lux. Now, the controlled variables R, distance between light and the light meter, and experimenting environment. Here is a diagram of my setup. Keep in mind that the lights were turned off while conducting this experiment.